years ago. At that time began the scientific conception of the universe. You've all heard of Copernicus and his astounding conclusion that rather than the Earth being the center of the universe and the sun and the stars rotating around it, it was just the opposite. The Earth and all the planets were rotating around the sun. This scientific progress continued with the work of Galileo and Kepler and Newton. And they realized that the natural objects of the universe follow very, very simple natural laws. Just like we all know as we're sitting here, we feel a weight, we feel ourselves being pulled into the seat, and we call it the force of gravity. It's just a name. We can figure out an equation, a mathematical equation, which tells us how fast will something move if you let it drop. How much force will the Earth exert on us as we're sitting down or as we're standing? What will happen if we jump up? How quickly will we come down? And what Galileo and Newton did is they applied those equations not only to objects on the Earth, they made an astounding leap, and they said, you know what? Let's apply the same equations to the motion of those heavenly orbs that we see. And they discovered that, in fact, the motion of the moon and the motion of the Earth around the sun could all be explained precisely by the same simple equation that governs how things move on Earth and how they fall and how fast they fall. It's exactly the same phenomenon governed by exactly the same equation. And that's totally radical. It's chutzpah to think that you can explain the heavenly motions by a simple law. But immediately what happened is the conception of the universe changed. Instead of having these spiritual entities moving around in perfect circles at the behest of God, you had these planets made of material just like the Earth is made, moving around as a result of the laws of gravity, just like the laws of gravity operate on Earth. Let me tell you a little bit about how that works. If you have gravity pulling down an object towards the surface of the Earth, straight down, it will fall straight down. If you throw it like this, then we all know it makes some kind of trajectory and land again on the Earth. Since the Earth is curved, if you throw it fast enough, then it'll fall down somewhere down over here. If you throw it even faster, by the time it has fallen down, it will have gone a little bit past the horizon already. And you can see maybe where that's leading. If you throw it fast enough, it'll go all the way around and then back. If you throw it even faster, there's a certain speed at which the speed at which it falls is countered by the motion sideways. It's moving sideways because you shot it sideways, and it's moving in towards the Earth. It's moving in this direction because you threw it, but the Earth is pulling it in. It tries to move again in the direction that you threw it, but the Earth is pulling it in. At a certain speed, it will exactly make a circular orbit, or an elliptical orbit. What Galileo realized about nature is that although on Earth we see things move and then slowly come to a stop, the reason it comes to a stop is only because there's friction. There's air pushing against it, it's moving on the ground. There's always something obstructing the motion, and that's the reason that things come to a stop. Left to their own devices, nothing would go to a stop. Things would continue forever, particularly, for example, in the vacuum in space, where there's nothing obstructing anything. There's no reason for them to stop. Now, what would happen, for example, on the Earth, if I throw something up, it comes down. If I throw it at an angle, it goes in a trajectory like this and comes down. If I throw it harder, faster, it'll go that much further before it comes down. Imagine that I throw something really, really, really fast. Maybe I shoot a projectile from some type of a ballistic rocket or a bullet or something like that, and I shoot it straight out. Now, we know the Earth is curved. If I shoot it straight out, if I shoot it fast enough, before it manages to fall to the ground, maybe it'll kind of miss the ground. It'll miss the Earth and go off like that. Okay, but eventually probably it would hit like over here on the other side. Okay, again, here's the Earth. We're shooting it this way. It's trying to go to the ground, but it's going so fast that it kind of hits the ground over here. You can see the possibility that if I shoot it fast enough, what will happen is that it will kind of escape the Earth. Now, I could shoot it and it goes far away, or what could happen is it goes into orbit. What does orbit mean? Orbit simply means that it's falling towards the Earth, but while it's falling, it's also moving sideways because you gave it some kind of speed in that direction. So it's trying to move this way because you shot it this way, but it's also moving down because of gravity. But it's still trying to move this way, but it's also moving down because of gravity. It's still trying to move this way, but it's moving down. Here's the Earth towards gravity. It's still trying to move this way, but the gravity is pulling it in. It's still trying to move this way, but the gravity is pulling it in. If you think about it carefully enough, you'll see that there's a possibility of an actual orbit. And that is, in fact, how satellites stay up they're actually falling towards the Earth all the time. They're constantly falling towards the Earth. We're in orbit now about the sun. The Earth is falling into the sun. Don't get panicked. Right now, as we speak. The Earth is constantly falling into the sun. Because it has a speed in that direction, though, as it falls, it goes out. As it falls, it goes out. As it falls, it goes out. And it's exactly the right speed to take it into perpetual orbit. And this is something that the work of Kepler and Galileo, Tycho Brahe, with incredible observations and meticulous recording of all the times and positions of all the lights in the sky. And this understanding was given a formalistic basis by Newton. And what happened was something really absolutely astounding. Newton observed that gravity acts on the Earth. We all feel gravity. We're all pulled into our chair right now. We know that things will drop to the ground. And he showed that the very same formula that describes this action of gravity here on Earth describes the force that pulls, for example, the moon into the Earth, into the orbit of the Earth. He was able to calculate, based on the formula, if I were to drop this and to measure how fast it's moving at what time and so on, he came up with a formula that described the attraction of gravity. And he applied that formula to the moon and to the Earth, and he found that it exactly predicted the orbit of the moon. And then he tried it on the Earth and the Sun, and it exactly predicted the orbit of the Earth around the Sun. And that's pretty astonishing, to find that the same simple formula that describes this so familiar phenomena of gravity also is responsible for or describes this incredible heavenly motion.